Hello everyone, I am Pei Zhang from Tianjin University, IEEE Fellow. I also serve as an AAIA Fellow and a CSEE Fellow, and my work focuses on intelligent computation for modern power systems. The cover uses the Tianjin University identity, my contact information, and the laboratory account to establish the academic and engineering context of the course. Smart power system computing is not only a name for faster algorithms, it is a research direction that asks how a grid with renewable generation, power electronics, complex loads, and large-scale network data can still be calculated, optimized, and simulated with reliability. In this lecture, I use the contrast between Newtonian and Keplerian scientific paradigms as the organizing idea. Newtonian methods build equations from physical laws and solve them with numerical algorithms. Keplerian methods learn patterns from data and use those patterns for prediction. My position is that power systems need both physics for trust and data-driven learning for speed and adaptability. That combination also defines the audience for the course. I am speaking to students who need to understand why an algorithm works, and to engineers who need to judge whether a result can be trusted in a control room or planning environment. The course is organized around 5 connected questions. First, I define the scientific problems behind power system intelligent computing because power flow, optimal power flow, and time domain simulation are different mathematical tasks and they create different computational bottlenecks. Second, I examine power flow computation through Newtonian and Keplerian paradigms. Third, I do the same for optimal power flow, where nonlinearity and non-convexity are more severe because economic objectives and security constraints must be satisfied together. Fourth, I discuss time domain simulation, where differential algebraic equations and small simulation time steps dominate the cost. Finally, I assemble these pieces into a research framework. The framework is the practical result of the lecture. It shows where physics-based models, neural networks, graph models, and hybrid mechanisms should be placed so that the grid calculation is not merely fast, but also interpretable, feasible, and usable for online operation. The order is intentional. I do not begin with a neural network architecture. I begin with a computational problem because the appropriate learning structure depends on whether the target is a static algebraic solution, a constrained optimum, or a dynamic trajectory. Scientific computing in power systems can be understood through 2 paradigms. The Keplerian paradigm starts from observation. It collects data, finds patterns, and extrapolates those patterns to new cases. Genetic engineering and image processing are shown as examples because the underlying pattern can be learned from large datasets. In power systems, this corresponds to neural networks that learn mappings from load and generation data to voltages, flows, trajectories, or control decisions. Its advantage is speed and flexibility, but its weakness is that it may know what tends to happen without knowing why it must happen. The Newtonian paradigm starts from first principles. It writes mathematical and physical equations, then solves them with numerical methods. Industrial and molecular simulations illustrate this approach. For power systems, Newtonian computation gives physical interpretability and reliable constraints, but the curse of dimensionality and heavy computation appear as the network becomes larger and faster dynamics are considered. Intelligent computing is motivated by the gap between these 2 paradigms. A useful research contribution usually changes the balance between these 2 columns. If a method only reproduces historical data, it remains fragile. If it only solves equations slowly, it may remain impractical for online use. 3 core power system problems appear together because they are the computational foundation of planning and operation. Power flow computation solves large-scale nonlinear algebraic equations. The variables are bus voltage magnitudes and phase angles, and the equations express active and reactive power balance through the network admittance matrix. Optimal power flow adds an objective, usually generation cost or operating loss, and then imposes equality and inequality constraints. That turns the task into a large-scale nonlinear non-convex optimization problem. Time domain simulation is different again. It solves high-dimensional nonlinear differential algebraic equations where generator dynamics, stator algebraic equations, network equations, and control equations evolve with time. The diagrams also connect these mathematical forms to business and engineering work, market dispatch, stability assessment, emergency control, and operation analysis. A single intelligent computing framework must therefore handle algebraic solution, constrained optimization, and dynamic simulation. Treating all 3 as one generic artificial intelligence task would miss the physical structure that operators depend on. The formulas in the background are not merely examples. They indicate which variables a learning model must respect. Bus voltages, phase angles, admittance parameters, generator outputs, and dynamic states. These are the quantities that connect computation to the physical grid. The Newtonian power flow formulation begins with circuit laws. The compact equation I equals YV means that bus current injection is determined by the admittance matrix and bus voltage vector. Complex power at bus I is SI equals VI times the conjugate of II, so active and reactive powers become nonlinear functions of voltage magnitudes and phase angles. Backward-forward sweep uses distribution network topology. In the backward sweep, branch currents are accumulated from downstream loads. In the forward sweep, node voltages are updated through branch impedance drops. This is efficient for radial distribution feeders. Newton-Raphson uses a different idea. It builds active and reactive mismatch equations, linearizes them through a Jacobian matrix, solves a correction equation, and updates voltages until the mismatch is small. The two flowcharts explain the engineering trade-off. Backward-forward sweep is simple and topology-aware for radial systems. Newton-Raphson is general and powerful for mesh transmission systems, but it depends on a well-conditioned Jacobian and good convergence behavior. The Jacobian terms also explain sensitivity. The partial derivative of active power mismatch with respect to angle or voltage tells the solver how a small state change affects balance. This local sensitivity is exactly what a purely learned model often lacks. The challenge table translates algorithmic complexity into grid scale. A system with 1,354 nodes already produces a Jacobian dimension of 2,447 by 2,447. When the system grows to more than 13,000 nodes and 11 voltage levels, the Jacobian grows to more than 23,000 by 23,000. Sparse matrix methods reduce storage and computation, but singularity and ill conditioning remain practical problems. Distribution networks add another difficulty. Their resistance to reactance ratios are high, so the assumptions that work well in transmission systems can become weaker, and the numerical equations may converge slowly or fail. This is why intelligent computing is attractive. Operators need fast answers for very large systems, but they cannot accept answers that ignore physical feasibility. The page therefore defines the pain point for hybrid methods. Data-driven models may accelerate repeated cases, while Newtonian equations still provide the structure that prevents meaningless voltage and flow predictions. The business consequence is direct. If one operating snapshot takes too long, operators cannot test many contingencies, renewable scenarios, or switching plans. Computation speed therefore becomes part of reliability, not only part of software performance. Keplerian power flow methods replace repeated equation solving with learned mappings. ADNN can take active and reactive injections, network parameters, or historical operating states as inputs and predict voltage or flow outputs. ACNN treats structured measurements like a feature map, which can be useful when the data can be arranged into grid-like patterns. AGCN and AGNN are more natural for power networks because the grid is a graph, buses are nodes, lines are edges, and electrical connectivity determines how information should pass between neighboring buses. The four model sketches emphasize that the output is not an abstract class label. It can be bus voltage, branch line flow, phase angle, or another physical quantity needed for operation. The engineering value is speed after training. Once the model has learned the mapping, inference may be much faster than iterative numerical solution. The risk is that the learned model may be accurate only inside the operating domain represented by the training data. The graph-based models are especially important because the same neural architecture can be transferred more naturally across networks with different sizes. A bus does not need a fixed position in an image, it needs its electrical neighbors and parameters. The limitations of data-driven power flow are shown with a network diagram and a feasible solution space plot. Large volumes of high-quality data are required, but power systems do not operate uniformly across all possible states. Many operating points are rare, unsafe, or never observed. If a neural network is trained on a narrow region, it may interpolate well but extrapolate poorly. Physical mechanisms are also difficult to explain in black box models. A voltage prediction can look numerically close while still violating Kirchhoff's laws or branch limits. Large grids make the input dimension high, and training cost can increase rapidly. Parameter drift is a further issue. Transformer tap changes, network reconfiguration, renewable plant changes, or topology updates can shift the relationship learned by the model. Retraining every time is not operationally attractive. The feasible space figure highlights why sample selection matters. Training samples must cover the physical solution space, not just a convenient historical dataset. This motivates physics-informed learning and topology-aware models. A good training strategy must deliberately include boundary cases, high loading, weak voltage support, topology changes, and renewable extremes. Otherwise, the model may be accurate in comfortable conditions and unreliable when operators need it most. Optimal power flow begins with the same physical equations as power flow, but it adds an optimization target. The objective function minimizes active power generation cost, represented as a quadratic function of generator output. Equality constraints enforce active and reactive power balance at every bus. Inequality constraints impose lower and upper limits on generator active output, reactive output, bus voltage magnitude, reactive compensation, and branch apparent power. These constraints are not decorative. They represent generator capability, voltage security, equipment thermal limits, and network feasibility. The left model explains why OPF is difficult. The objective is nonlinear, the constraints are nonlinear, and the feasible domain is non-convex. The right flowcharts compare Newton and interior point solution paths. Newton-based methods form Hessian and Jacobian matrices, solve correction equations, and check KKT convergence. Interior point methods add barrier or perturbation logic and update primal and dual variables. Both rely on accurate mathematical structure, but their computational burden grows sharply when the system scale and constraint count expand. Each inequality has a different operational interpretation. Generator limits protect equipment capability. Voltage limits protect service quality and stability margin. Branch flow limits protect thermal security. Reactive limits decide whether voltage support is still available. The tables quantify why online OPF is still hard. For a 1354 bus model, the optimization already contains tens of thousands of continuous variables and integer variables, plus hundreds of thousands of inequality constraints. For a 10,000 bus model, the number of continuous variables rises above 200,000, integer variables exceed 600,000, and inequality constraints reach more than 9 million. The benchmark study then shows commercial solver behavior. On some large test cases, IPOPT convergence rate drops to zero, and computation time becomes far beyond what online operation can tolerate. The lesson is not that commercial solvers are weak. The lesson is that full nonlinear constrained optimization at this scale can exceed the real-time requirements of dispatch. Intelligent computing must reduce repeated computational burden, warm start or guide the solver, learn active constraint structure, or predict near-feasible solutions while keeping enough physics to satisfy operational rules. This is why hybrid OPF should be evaluated by both time and feasibility. A method that saves seconds but creates violations is unacceptable, while a method that predicts a good warm start may still be valuable even if a solver performs the final correction. Keplerian OPF methods try to learn the relationship between operating conditions and optimal solutions. ADNN can map loads, renewable injections, and network parameters to generator dispatch or voltage setpoints. An RNN is useful when the operating condition has temporal dependence, because dispatch decisions across time are not independent. A CNN can learn structured features when the data representation has spatial or matrix-like organization. A Hopfield neural network has a different historical role. It treats optimization as an energy minimization process and can be used to search for solutions. The practical attraction is clear. If the model can predict an OPF solution quickly, online decision support becomes more feasible. But prediction alone is not enough. The predicted dispatch must respect equality constraints, inequality limits, and the economic objective. A low-cost prediction that violates voltage or branch limits is not a solution. Therefore, pure data-driven OPF must be strengthened with physical feasibility checks, constraint-aware loss terms, or hybrid solver interaction. Temporal models are particularly relevant when renewable forecasts and ramping limits matter. The optimal action at one interval affects the feasible region at the next interval, so a sequence-aware model can capture information that a one-shot predictor may miss. The OPF challenge list is mainly about trust. Heuristic methods may avoid some mathematical difficulties, but they often require many iterations and can still be slow. Data-driven methods are fast during inference, yet their performance depends heavily on training data quality. If the future operating scenario was not represented during training, a learned model may not generalize. This is especially dangerous in OPF because the output is not just a number, it is an operating decision with security consequences. Pure learning also lacks a deep understanding of the physical essence of the problem. A black box model may learn historical correlations between load levels and generator outputs, but it may not know why a voltage limit becomes binding or why a transmission corridor constrains active power transfer. Interpretability matters because operators must justify decisions. In engineering terms, the model must answer two questions at the same time. Is the result economically good? And is the result physically feasible under the actual network state? For deployment, interpretability also affects accountability. When an operator asks why a generator output is recommended, the answer should refer to constraints, cost, and physical margin, not only to a hidden layer activation. Time domain simulation changes the mathematical object from static equations to dynamic trajectories. The generator dynamic equations describe how internal transient voltages, rotor angle, and speed deviation evolve over time. The first two rows describe transient voltage dynamics along the d and q axes. The third row links rotor angle derivative to speed deviation. The fourth row describes acceleration, where mechanical power, electrical power, damping, and electromagnetic coupling determine speed change. Stator voltage equations connect internal generator states with terminal voltage and stator currents. Network power flow equations then couple generator currents and bus voltages through the reduced admittance matrix. The two solution methods show why computation is expensive. Implicit trapezoidal integration solves implicit equations at each time step. Runge-Kutta computes intermediate slopes such as k1 through k4 before updating variables. In stability analysis, accuracy depends on small time steps and repeated updates. The Newtonian paradigm is physically faithful, but high-dimensional dynamics make large-scale real-time simulation difficult. The matrix form is useful because it separates differential states from algebraic coupling. Even when a neural model is introduced, it should respect that some variables evolve by dynamics while others are solved from network constraints at each instant. Power electronics have changed the dynamic nature of the grid. Traditional electromechanical transient simulation can often use millisecond-level time steps. When converters, fast controls, and electromagnetic transient behavior dominate, the required time step may shrink toward microseconds. That difference is not a small numerical detail, it multiplies the number of simulation steps by orders of magnitude. The table makes the scaling visible. A 1951 bus system already includes thousands of state, control, algebraic, and differential variables. A 13,659 bus system expands these counts dramatically, with more than 54,000 algebraic variables and more than 36,000 differential equations. Each simulation step updates these variables and solves coupled equations. The computational pressure becomes severe when operators need many contingency simulations, probabilistic scenarios, or online stability assessment. Intelligent computing is therefore asked to preserve dynamic accuracy while reducing repeated numerical burden and enabling faster scenario screening. Fast dynamics also change model validation. It is not enough to match a final stability conclusion. The transient waveform, peak deviation, damping behavior, and timing of control response can all influence whether a protection or control strategy is acceptable. Keplerian time domain simulation uses data-driven models to predict state trajectories instead of solving every differential algebraic equation at every small time step. The ELM diagram shows a feed-forward learning structure with input, hidden, and output layers. Extreme learning machines are attractive because some parameters are randomly assigned and output weights can be solved efficiently, giving fast training compared with deeper iterative models. The ensemble online sequential ELM diagram extends this idea to rolling trajectory prediction. Multiple fitted functions process past fault or post-fault trajectories. Rolling prediction functions estimate future states, and the results are assembled into an extrapolated value. For engineering use, the target is not only a stability label. Operators may need voltage, angle, speed, or other state trajectories across time. The data-driven approach can reduce computation cost, but its credibility depends on whether the training simulations cover the disturbances, operating points, and control actions that will appear in real operation. The online sequential form is valuable because operating data arrive continuously. A model that can update its prediction as new trajectory samples arrive is more useful than a static model that only works for a fixed pre-computed dataset. The data-driven simulation challenge is generalization under disturbance. Large faults, rare contingencies, and extreme operating conditions are exactly the cases that matter most, but they are also the hardest to observe in measured data. Purely data-driven models can struggle to capture highly coupled dynamic behavior because the interaction between generators, converters, controls, and network algebraic equations is governed by physical structure. If the training set lacks a certain fault type or operating condition, prediction accuracy may degrade precisely when the system is under stress. Another limitation is research focus. Many existing studies learn the mapping from disturbance conditions to stability outcomes. which supports rapid stability evaluation, but does not fully replace time domain simulation. A stability label answers whether the system remains stable. A simulation trajectory explains how voltage, angle, and frequency evolve. For operation, both are valuable. The research opportunity is to combine trajectory prediction with physical constraints so that speed does not come at the cost of dynamic realism. The difficult cases are the ones near the security boundary. There, small prediction errors in rotor angle, voltage, or frequency can change the stability judgment. Physical constraints help reduce that risk by narrowing the space of plausible trajectories. The integration diagram summarizes the argument. Newtonian computation contributes clear physical laws, rigorous numerical computation, and high result certainty. Its weaknesses are high modeling complexity, slow computation speed, and heavy resource demand. Keplerian computation contributes flexible and adjustable modeling, fast calculation, and suitability for dynamic and complex scenarios. Its weaknesses are lack of physical interpretability, reliance on high-quality data, and weaker generalization. Power system intelligent computing should not choose one side as a replacement for the other. The goal is integration. By combining both paradigms, I want enhanced physical interpretability and result reliability, improved accuracy with real-time performance, stronger generalization for unknown and extreme conditions, scalable response to dynamic system requirements, and adaptability to complex scenarios and ultra-large systems. This is the central design principle of the course. Hybrid methods must be evaluated not only by benchmark accuracy but by whether they improve the operational trade-off among trust, speed, scalability, and adaptability. This integration also changes how I judge innovation. The strongest method is not necessarily the deepest network or the most complex solver. It is the method that places mechanism and data at the location where each contributes the most. For power flow, the combination of Newtonian and Keplerian paradigms can be implemented in guided mode or embedded mode. In guided mode, the topology-gated physics-informed neural network uses grid topology and physical equations as regularization terms. The inputs include generation and demand quantities together with topology information. The network does not learn freely from data alone. Physical residuals guide the learning process, and a gate mechanism adjusts network parameters according to topology. The output includes active power, reactive power, voltage magnitude, and phase angle. In embedded mode, the model-driven graph convolutional network inserts a linearized power flow model into graph convolution propagation. That means the graph aggregation is not just a generic message passing rule. It is guided by electrical connection relationships and power flow coefficients. The engineering value is stronger generalization. If topology or loading changes, the model has a physical reason to adjust its prediction rather than relying only on historical similarity. Power flow learning becomes a physics-aware estimator, not a black box shortcut. The gate mechanism is especially important for topology variation. If a line is switched, the model should not treat the case as a completely unrelated sample. It should adapt the information path according to the changed electrical graph. The power flow research contents can be read as a checklist for usable intelligent computation. I need neural network architectures that perform both convergence determination and solution computation. Convergence determination matters because operators must know whether the numerical problem is solvable before trusting the predicted solution. I also need methods for embedding physical models and principles, KCL, KVL, grid topology, network parameters, power electronics models, and discrete physical behaviors such as tap changes or switching. Sample selection is another research task. The training set should cover the solution space, not merely repeat easy historical operating points. Finally, generalization must be tested under changing topology and parameter conditions. This is where many learned models fail. A model that performs well only on one fixed test feeder is not enough for practical deployment. The research direction is therefore architecture plus physics plus sample design plus stress testing. These research tasks also define experimental design. A paper should not report only average error. It should test convergence classification, solution residuals, topology transfer, parameter drift, and violation rates under stressed operating cases. For OPF, guided and embedded modes target physical feasibility and optimality. In guided mode, physics-informed deep learning learns an input-output mapping but uses physical information as a regularization term. The figure reconstructs input power demand through the predicted optimal voltage, angle, active generation, and reactive generation. If the reconstructed demand does not match the original demand, the loss increases. This forces the model to respect power flow consistency. In embedded mode, the physics-guided graph convolutional neural network constructs physical features and loss functions before prediction, load, renewable energy, and topology change enter the model-informed feature construction. The graph convolution network then learns on a representation shaped by the grid, not on raw data alone. The OPF solution produced at the end must satisfy both economic and physical requirements. For business value, this hybrid design can support faster dispatch screening, active constraint prediction, warm starts for solvers, and online decision support while reducing the probability of infeasible learned commands. The demand reconstruction loop gives the model a physical audit. If predicted controls cannot reproduce the input demand through the power flow equations, the solution is internally inconsistent, even if the direct numerical error appears small. The OPF research contents emphasize feasibility, generalization, and global quality. Embedding physical constraints into neural networks and reinforcement learning models is necessary because a learned dispatch is only useful if it satisfies actual grid limits. Sample optimization and loss function design address the data side of the problem. Training samples should include normal, stressed, and boundary operating points so the model learns where constraints become active. Loss functions should punish violations in a way that aligns with operating priorities, not merely minimize average numerical error. Efficient reward functions are needed when reinforcement learning is used because the reward must balance cost reduction, voltage security, line limits, generator capability, and convergence behavior. The phrase global optimality is important. A fast model that regularly finds local or infeasible decisions may be worse than a slower solver. The hybrid research target is speed with reliable quality, not speed alone. Reward design in reinforcement learning is particularly delicate. If cost receives too much weight, the agent may learn unsafe decisions. If penalties dominate too strongly, the agent may become conservative and fail to exploit available operating flexibility. Time domain simulation uses three fusion modes: guided, embedded, and parallel. In guided mode, physics-informed Kolmogorov-Arnold networks place physical constraints into the KAN loss function. The diagram includes dynamic prediction, parameter identification, boundary condition errors, and the loss threshold. The physics residual, such as a differential equation residual, prevents the network from producing a trajectory that only fits data but violates dynamics. In embedded mode, PINN-SIM embeds a physics-informed neural network inside a traditional simulation method. The neural network estimates state variables and system parameters, allowing a larger time step while keeping the physical model active. The small equations around the center represent residual minimization and correction of model parameters. In parallel mode, PI-NU-DYE combines a physics model and an ODE net in a closed-loop simulation. Measurements drive both internal system and external system components, and adjoint dynamics support continuous backpropagation. The shared engineering target is faster dynamic simulation without losing physical trajectory credibility. The three modes serve different use cases. Guided learning is suitable when physical equations are available as residuals. Embedded learning is suitable when a neural component can accelerate a numerical step. Parallel learning is suitable when physical and external data streams must interact continuously. The time domain research contents focus on dynamic accuracy and scalability. Physical principles must be embedded into neural networks so that predicted trajectories remain realistic during simulation. This is especially important for faults, converter controls, and fast transients, where a visually smooth curve may still be physically wrong. Scalable neural network architectures are needed because modern power systems contain many dynamic states and many algebraic coupling variables. A method that works on a small benchmark may not meet real-time needs for a regional or provincial grid. Sample selection must balance generalization capability and training efficiency. Extreme scenarios cannot be ignored, but generating every possible contingency is impossible. The final task is to explore diverse fusion modes. Some problems need physics to guide a loss function. Some need neural components embedded in numerical solvers, and some need parallel interaction between physical and learned models. A convincing simulation method should therefore report more than speedup. It should report trajectory error, physical residuals, robustness under unseen contingencies, and performance as the network dimension increases. The framework page connects scientific problems, research modes, and computation tasks. At the top, the three problem classes are large-scale nonlinear algebraic equations, high-dimensional nonlinear differential algebraic equations, and large-scale nonlinear non-convex optimization models. Across the middle, Newtonian and Keplerian paradigms are combined through serial, parallel, guided, embedded, and feedback modes. Serial mode sends mechanism output into a data model. Parallel mode combines mechanism and data paths through a coupling operator. Guided mode uses mechanism as a constraint on data learning. Embedded mode places mechanism inside the data model. Feedback mode lets data correct or update the mechanism. At the bottom, the framework maps these modes to power flow analysis, time domain simulation, and OPF calculation. The research agenda is practical. Solve convergence and solution computation in PowerFlow, ensure dynamic accuracy and scalable architecture in simulation, and embed physical constraints and rewards in OPF. This is a roadmap for intelligent computing that remains grounded in power system physics. Feedback mode is important for future grids because mechanisms themselves may need correction. Parameters drift, converter controls change, and measurements reveal model mismatch. Data can then update the mechanism while the mechanism still constrains the data. I close with the core message of the course. Smart power system computing is the integration of physical mechanisms and data-driven learning for grid calculation, optimization, and simulation. Newtonian methods gives the equations, constraints, and interpretability that power systems require. Keplerian methods provide speed, adaptability, and the ability to exploit operational data. The engineering challenge is to combine them in the right mode for the right problem: guided or embedded learning for PowerFlow, constraint-aware hybrid learning for OPF, and physics-informed or parallel structures for time domain simulation. With that integration, intelligent computing can support faster online analysis, more reliable dispatch, stronger stability assessment, and a better adaptability to renewable and power electronic-dominated grids. Thank you. The practical goal is a computing system that gives operators answers quickly enough to act, with enough physical meaning to trust, and with enough adaptability to handle the changing grid.